Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we are going to solve vending machine. This prompt states, write a function that returns an integer for the smallest number of coins required to make change. If a combination is not possible, then we return -1. So we're given the denominations of change, and then we're given a target change amount that we want to find the smallest number of coins that we can use to reach this change amount. So for this first example, we call the function min coins for change, we pass it the denominations and the change amount, and we want to reach 12, and we have coins of 1, 5, and 10 available to reach this amount. The smallest number of ways that we can get here is 1 10 coin and 2 1 coins, or 10 plus 1 plus 1 is 12. For this second example, we have a target of 53, and we have the coins 5, 10, and 25 available, and none of these coins can add up to reach 53. So the output is -1, which indicates we can't reach this target amount with the coins available. Let's take a look at one more example, and then we can start to build up some intuition about how we would solve this. We're going to use a target change amount of 8, and we want to find the smallest number of ways to reach 8 using a coin with a value of 2 and 3. If you were solving this in your head, you would probably do something like, well, I know 2 plus 2 plus 2 plus 2 is 8, so that's going to be 4 coins. But I also know 3 plus 3 is 6, and then plus 2 is 8, so that's smaller, so I can get there in 3 coins using that combination. Or maybe you approached it the other way. You start at 8, and then you start subtracting coins until you reach 0. So 8 minus 3 is 5, minus 3 is 2, minus 2 is 0, so that's 3 coins, or 8 minus 2 minus 2 minus 2 minus 2 is 0. In either approach, what you're doing is just trying different combinations of coins and then using the information about what a value adds to and what that is relative to 8 makes the decision on what next coin you try. So if we did 2 plus 3, we know that's 5, so we can quickly see that 8 minus 3 is 5. So then if we add one more 3 coin, that's going to be 8. So 2 plus 3 is 8. And then the approach is very similar when we subtract. We try different denominations, and we try to reach 0. So this thought process of where we're trying to build up the solution and trying different denominations at each point to reach the target, this is almost identical to a bottom-up approach using dynamic programming or a top-down approach using dynamic programming. So let's explore that, and we'll start with the bottom-up approach. So we know with dynamic programming, we're solving subproblems. We're making a decision at each point that will give us the optimal solution based on the current value and the solution to previous subproblems. And then we memoize these solutions and build this up throughout the solution until we reach the final value, which will be the overall answer. So let's first visualize how this looks before we start looking at actual numbers. We start at 0, find the solution there, then we move forward. At each point, we're memoizing the solution to the subproblem, and then we can use that subproblem solution in future subproblems. Once we reach the end, this final value is the solution to the question because we found it using the answers to all the prior subproblems, which we built up along the way. The way dynamic programming is going to work for this question is we're going to find the minimum coins for every change amount, starting at 0, and then each value all the way up to the target. So we find the minimum number of coins to reach 0, then min coins to reach 1, min coins to reach 2, min coins to reach 3, min coins to reach 4, 5, 6, and so on, until you reach the last item, which is 6 in this case. And the way it's going to work is that when we know the min coins to reach prior values, as we continue to try different combinations of coins, we can use the smallest number of coins that we saw reach prior values to then determine how we reach the current value with the smallest number of coins. And since the values we're looking to calculate are just sequential integers from 0 up to the target, we're just going to use an array to memoize those values. So we store the optimal answer at each point, which corresponds to the index in the array. So let's see how this actually works. Let's go back to the example where we have a target of 8 with the denominations of 2 and 3. There's only 2 ways to reach 8. That's by using a 2 coin from the value of 6, or by using a 3 coin from the value of 5. With these 2 denominations, those are the only 2 possible ways to reach this final amount. So if we know we can reach 8 from only 2 spots, then all we have to do is find the minimum number of ways to reach 6 and 5. So again, we would check what happens when we use a 2 coin to reach 6 and 5, and then a 3 coin to reach 6 and 5. Which moves us backwards through the memoization data structure. But this is the subproblem we're solving. If we try all the coins at all the target values, this is how we can solve the subproblem. When we use the smallest number of ways to find each point before the current, we can just subtract the denomination to see the possible ways to get to this current value. Once we solve this subproblem, all the way up to the target, we're done. And at each point, we're simply trying one additional coin, or seeing how we could reach each point by using one of the available denominations at each step. So we saw to reach 8, we could get there from 6 or 5. But then to reach 6, we could get there from 4 and 3, because we take 6 and subtract the coins we have available. So we could get to 6 with a 2 coin from 4, or get to 6 from a 3 coin from 3. Then the other option is 5. We can subtract 2 from 5, and find the smallest number of ways to get to 5 from 3, because that's using a 2 coin, or the smallest number of ways to get to 5 from 2, because 2 plus 3 is 5. So this again just shows the subproblems we're solving. To reach 8, we try the denominations at the amounts before, based on the coin values. Then to reach those spots, we check the smallest number of coins to reach the prior spots again, using those denominations, and so on. So we continue to branch and solve these subproblems to find the smallest number of ways to reach each point. So this is dynamic programming. Each step is a decision, and we make the best choice based on the input amount and the denominations available, and how they add to the smallest amount calculated at previous subproblems. So for the bottom-up approach, we start at 0, and then we step forward by 1 value each time, and calculate the minimum number of coins to reach each change amount all the way up to the target. So after we calculated change amount, we memoize that value, and then at each current amount, we subtract all the denominations to look backwards and find the smallest number of ways to reach the current amount if we used any of the denominations to get there. So at each point, we're trying one additional coin to get to the current target amount. So we build up the solution along the way, and at each point, when we try to solve it, we take the current amount, so here at 5, we subtract 2 and 3, and then we look backwards in the memoization data structure to see how we could reach 5, which means we're trying each denomination once to reach the current spot. So we try all the possible coins at all the target values from 0 to 8. And this might sound like a lot of work to try all the coins at all the target values to get all the combinations, but this is really how dynamic programming works. You build up the solution and solve this subproblem of trying all the coins at each target, and then you memoize the solutions to remove duplicate work. So let's first see how we can reach 8 with only a 2 coin. 0 is always initialized to 0 because there's not a 0 coin, so there's no combination that can reach 0. We can't get to 1, but we can get to 2, and that's 1 coin, so the minimum number of coins to reach 2 is 1. Then to get to 4, it's 2 coins, so 2 plus 2, and then the minimum is 2 coins to reach this amount. To get to 3 coins, it's 4, or 2 plus 2 plus 2 is 6, so the smallest number of coins to reach this spot is 3. Then to reach 8, it's 2 plus 2 plus 2, or 3 coins, plus 2 is 4. So the smallest number of coins to reach 8 is 4. So what we're doing at each step is looking backwards through this memoization data structure to see the minimum number of ways to reach the current spot. So for example, let's say we're trying to solve the 6th subproblem, or reach a value of 6. The only denomination we have is 2, so we take 6 minus 2, and that gets us to 4. We saw we could get to 4 with 2 coins, so we're looking back through this memoization data structure. All we need to know is the number of coins. Because we don't care what combination got there, we just care that we could get there, and we want to know the minimum number of coins. In this case it was 2, but visually to see that, it was 2 plus 2 is 4. So then to reach 6, we know it takes 1 additional coin, so that 2 coins plus 1 for the denomination is 6. So the minimum number of ways to reach 6 is 3. And this is just the subproblem we continue to solve at each point. We try the available denominations and add those to previous values to reach the current item. And at each subproblem, it's always just plus 1 coin. We're checking the 1 additional coin we need based on the possible denominations to reach the current item. So we take the minimum coins, take the current amount, subtract all the coin values, and then we keep the minimum number of coins to reach the target value, and we continue to do this all the way up to the final target, which is the solution. Now that we have some intuition for the bottom-up dynamic programming approach, let's walk through it step by step. We're going to take the same example, where we have the coins of 2 and 3, and then a target value of 8. This top table is just used to visualize the combination of coins we'll be using, but this bottom data structure is the array that's going to store the minimum number of coins at each point. We initialize it to 0 because no combination can reach 0, so this is just the bottom case. And then we initialize all the other values for all the amounts from 1 up to the target to the largest integer in our language. Here we're going to call it infinity, but it's just going to be whatever the largest integer is in your language. We'll see why this is in a few slides, but just know this is the data structure, or the array, where we memoize the smallest coins required for each amount up to the target. So in the bottom-up case, we start at 0. There's no combination of coins that can reach 0, so 0 stays in the data structure, and we move on. We can't reach a value of 1 because both coins are larger than 1, so we continue. Then we reach a value of 2, and we start subtracting the coins, or each denomination, from this value, which allows us to look backwards in the memoization array. So 2 minus 2 is 0. The minimum number of coins to reach 0 is 0, so it's just 1 coin, which is the 2 coin. Then for 3, 2 minus 3 is negative 1, so it's not valid, so there's not an answer. So the solution to this subproblem is 1. The 1 2 coin, because we subtracted 2 minus 2 is 0, 0 plus 1 additional coin is 1. Then we get to 3. 3 minus 2 is 1. We didn't have a valid number of coins to get to 1, so we can't get to 3 using the 2 denomination. Then we do 3 minus 3, this denomination, which gets us back to 0. The minimum number of ways to reach 0 is 0, plus 1 3 coin. So the solution to this subproblem is 1, by using 1 3 denomination. Then we get to 4. 4 minus 2 is 2. We saw this took 1 coin. We add 1 additional 2 coin to this, and this gives us a valid solution to reach the target of 4. We do 4 minus 3 is 1. There's no valid coins to reach 1, so we can't reach the target of 4 using a 3 denomination. So the smallest number of coins to reach 4 is 2. Because we took the 2 denomination to reach 2, added 1 additional 2 coin, and that got us to 4. So 1 plus 1 additional coin is 2. Then we move on to 5. For this subproblem, we take 5 minus 2, which gets us to 3. We had 1 coin here, which is the 3 denomination. So 3 plus 2 is 5. So this is a valid combination of coins to get to this target. Then we try 3, so 5 minus 3 got us to 2. 2 plus 3 is 5. So again, we have a valid combination, which is 2 coins. So the solution to this subproblem is 2 coins. In either case, when we tried both the 2 denomination and the 3 denomination, they both got us to 5 using 2 coins, because when we looked backwards, at 3 we had 1 coin, we added 1 additional coin to it, which was the 2 denomination, so that's 2 coins. Or when we subtracted 3, that got us back to the 2 subproblem. There was 1 coin here, which was a 2. We add 3 to that, so 1 coin plus 1 more coin is also 2. Now we reach the 6th subproblem. You take 6 minus 2, which gets us to 4. Here we had 2 coins, so we add 1 additional coin, which we said is the 2 denomination. So the 2 coins, 2 plus 1 additional 2 is 3 coins. Then for 3, we take 6 minus 3, which gets us back to the 3 subproblem. This had a solution of 1, so 1 coin plus 1 additional 3 coin is 6, or 3 plus 3 is 6 for 2 coins. So 2 is smaller than 3. So we had 2 solutions to this subproblem, and they had different coin amounts, so we kept the minimum, which was 2 coins. So the solution to this subproblem is 2. Then we go to 7. We take 7 minus 2, which gets us back to 5. It took 2 coins to get to 5. We add 1 additional coin, which is 2. So this is 3 coins to get to 7. Then we take 7 minus 3. That gets us back to 4. 4 took 2 coins. When we add 1 additional coin, that's also 3. So the solution to this subproblem is 3. And then finally we reach 8. 8 minus 2 is 6. The optimal solution to this subproblem was 2 coins. So if we add 1 additional coin, 3 plus 2, or 1 additional 2 coin is 8. So this is a 3 coin combination to reach the target of 8. Then we do 8 minus 3. The solution to this was 2. We add 1 additional coin again. So 3 coins to get to 8. So the minimum number of coins to get to 8 is 3 in either case. And the solution to this subproblem is also the solution to the question. So to solve this question, we just found the optimal solution to each subproblem. And then along the way, we continued to build up the solution. So at each point, we had a choice. If I used either of these denominations with the solution to a prior subproblem, what's the smallest number of ways I can reach this point by adding 1 additional coin? And note that this top table is just to visualize the actual coin combinations we used, but we actually don't care about the combinations. We just care if we could reach a prior value, or there was a combination that led us to a prior value, and then if we add 1 additional coin, or try each denomination, to move from a prior amount to a current amount with that coin, how do we get there? So each step, we're just adding 1 additional coin. We're trying each denomination by subtracting it from the current amount, which means we're adding it to a previous amount, or the smallest number of coins, which is the solution to a previous subproblem. As long as we had any solution to a subproblem, we know we can add one additional coin to it to get to the current amount, and then we take the minimum of all the possible combinations and store that as the solution to the current subproblem. So we tried all the coins at all the amounts from 0 up to the target, and then at each point, we store the smallest number of coins to solve that subproblem. Each step is a decision, and the question is, should I use any of these denominations one more time to reach this current amount by adding that to a combination or a minimum number of coins to reach a prior amount? Once we solve all these subproblems, when we reach the end, it's also the solution to the problem. And that's the foundation of the logic for a bottom-up dynamic programming solution. That leaves us with just two open questions. The first is, what if there isn't a previous minimum or a solution to a prior subproblem when we subtract a coin to see how we can reach the current amount, or there's no combination of coins that can sum together to reach this current amount? And the other open question is, how do we know if we didn't have a combination of coins that can sum together to reach the target, so this invalid case? And this is the instance when we would return -1. And the answer to both of these is when we recognize that maximum integer value in a spot. So we said we initialized the memoization array using the largest integer value for all amounts from 1 up to the target. So if we look for the solution to a subproblem, and we see this largest integer, here we're calling it infinity, that means there wasn't a valid combination of coins to reach this spot. For example, we can't reach 5 using 3, 6, and 11. So we see infinity here. So after we try all the coin combinations for all the amounts from 0 up to the target, if the target is still this largest integer, then we return -1. So this is the case we're looking for. But then also when we're looking at subproblems, like we said in the case of 5, when we're at the target of 8 and we subtract this 3 coin to get back to 5, we know we're adding 1 coin to it, so that's infinity plus 1, and we compare that to infinity, which is already in the 8 spot. Well, when we take the minimum of both of those, it just stays infinity, so it stays as an invalid spot and one that we couldn't reach with the combination of coins. So for example here, when we reach 4, we saw that when we took the 2 denomination, we do 4 minus 2, that got us back to 2. We know we can add 1 additional coin, so this is valid. But when we did 4 minus 3, that got us back to 1. We saw infinity here, so we know this is an invalid spot, and when we try to add 1 coin to infinity, it's just going to stay infinity. So there's not a valid combination to reach 4 using the 3 denomination. We take the minimum of infinity plus 1 and 2. So the solution to this subproblem is 2. So for completeness, and to make sure we really understand what's happening, let's now take an example where we have 3 coins. We'll look at denominations of 2, 3, and 5, and we'll go to a target of 8. We initialize the memo array at 0 for the value of 0, and then the largest integer for all the other items. So we start at 0, none of these values can reach 0, so it just stays 0. We move to 1, all these coins are greater than 1, so when we take 1 minus 2, 1 minus 3, and 1 minus 5, they're all negative. And when we get a negative index value, we know it obviously can't be in the array, so it just stays as this infinity value or the max integer in your language. Then we get to 2, we do 2 minus 2 is 0, so memo of the I minus 2, which is 0. Then we add 1, because we're adding 1 more 2 coin, and we take the minimum of 1 and infinity. That's just 1 coin. So 1 is currently the solution to this subproblem. 3 and 5 are larger, so there's not a value that can reach this spot. Then we move on to 3. 3 minus 2, this denomination, gets us back to 1, which is infinity. The minimum of infinity plus 1 and infinity is infinity, so it doesn't change. We still don't have a valid combination. Then we check the 3 denomination. 3 minus 3 is 0. So 0 plus 1 or infinity is 1 coin. So that's currently the solution to this subproblem. Then we get to 5. 5 is larger, so there's no answer. So the solution to this subproblem is 1 coin, which is the 3 coin. So we memoize 1. Then we get to 4. 4 minus 2 is 2. The solution to this subproblem is 1. So 1 coin plus an additional coin, 1 plus 1. The minimum of 2 and infinity is 2. And to visualize it, the coins we used was a 2 coin, and then added the current 2 coin. So 2 is the solution to this subproblem because the smallest number of coins is now 2. Then we check 3. 4 minus 3 is 1. It's infinity. So the minimum of infinity, or 2, because 2 is what we previously calculated here, when we tried a prior denomination, it's still 2. So the solution to this subproblem does not change. 5 is still larger than this value, so when we do 4 minus 5, it's negative, there's no solution, and we continue. Then we reach 5. 5 minus 2 is 3. It was 1 coin to get to 3. So 1 plus 1 more additional coin, which is the 3 denomination plus the 2 denomination. We take the minimum of 2 and infinity. That's 2 coins. So that's currently the solution to this subproblem. Then we do 5 minus 3 is 2. So 1 coin plus an additional 3 denomination is 2. The minimum doesn't change because it's the same as we previously calculated. So it stays as 2 coins. Then we try 5. 5 minus 5 is 0. So 0 plus 1, or 0 plus the 5 denomination, 1 more coin. The minimum of 1 and 2 is 1. So now the solution to this subproblem is 1, because after we tried all the coins at this amount, 1 5 coin is smaller than the previous combination of coins. Then we get to 6. 4 is 2. 2 plus 1, 2 denominations plus 1 more 2 denominations is 3. The minimum of 3 and infinity is 3. So that's currently the solution to this subproblem. Then we take 6 minus 3 minus the 3 denomination. This gets us to the value of 3, which was previously 1 coin. So we're adding 1 additional coin. 1 plus 1 is 2. So the minimum of 2 and 3 is 2 coins. 2 is smaller than 3, which was previously stored there. So now 2 coins is the smallest number of coins to reach this amount. Then we do 6 minus 5. That's infinity. Infinity plus 1 is larger than 2, so the previous solution to this subproblem doesn't change. Then we reach 7. 7 minus the 2 denomination is 5. It took 1 coin to get to 5, so 1 plus 1 additional coin, which is the 2 denomination. The minimum of 2 and infinity is 2, so we store 2 as the answer to this subproblem. Then we subtract 3 from 7. This gets us the amount 4. It took 2 coins to reach 4. 2 plus 1 additional coin is 3. The previous answer we found of 2 is smaller, so it doesn't change. Then we do 7 minus the 5 denomination gets us to 2. The smallest number of coins to get to 2 was 1. So 1 plus an additional coin is 2. The minimum of 2 and 2 is still 2, so nothing changes. So the answer to this subproblem is still 2. Then we move on to 8. 8 minus the 2 denomination gets us back to 6. It took 2 coins to get to 6. So 2 plus 1 more additional coin, which is the 2 denomination. So the minimum of 2 plus 1, which is 3. 3 versus infinity. 3 is smaller. So the current answer to this subproblem is 3. Then we do 8 minus 3 for the 3 denomination. This gets us back to 5. The minimum number of coins to get to 5 was 1. We're adding 1 additional coin to that, so 1 plus 1 is 2. The minimum of 2 and 3 is 2 coins. This is a new minimum. So now we store that as the solution to this subproblem. Then we do 8 minus 5 is 3 for the 5 denomination. It took 1 coin to get to the value of 3. So 1 plus an additional coin is 2. This doesn't change the minimum. So the answer to this subproblem is still 2. But this is also the last subproblem, and it corresponds to the target we're looking for. So we found the minimum number of ways to reach 8 is 2 coins, and we did this by solving prior subproblems. We found the minimum number of coins to get to each spot, and then as we tried each denomination at each amount, when we reached 8 and looked backwards, we could add just 1 additional coin to a prior amount, which totaled 2 coins to get to 8, and 2 is the smallest number of coins to reach 8, which is the solution to the question. And finally, let's visualize and discuss the top-down approach and understand the overlapping subproblems. For this, I've slightly changed the parameters to make it a little easier to visualize. We're using denominations of 2, 3, and 7, and going for a target of 11. With the bottom-up approach, we started at 0, and then tried every value up to the target. In the top-down case, we start at the target, and then we recursively try the denominations going backwards until we hit 0, which is a base case. And when we find 0, this means we had a successful path where we had a combination of coins that could reach the target. If we reach a negative number, then this means it wasn't a valid combination, so in that base case, we just ignore it. So with bottom up, we went 0 to target, and then with top down, we go target to 0. With the top down case, we're again trying all the denominations at each point, but this time we're subtracting them at each subproblem. So we start at 11, we subtract 2, 3, and 7, which gives us 9, 8, and 4. And then at each of these values, we again subtract 2, 3, and 7. And we continue to repeat this process at all the nodes, where we subtract all the denominations until we reach the base cases that we discussed. And the red value indicates the minimum number of coins that it took to reach that spot. So you can either count up from 0 to the target, or from the target down to 0 and then use that number. Either way, you will still get the same minimum number of coins required. And here, notice we're using the number 99. We said previously we're using the largest integer. Here we're using 99 as that value, which we know is larger than any coin combination we could use, so it just takes that place. If we see a 99, it means there wasn't a valid combination, so it's just going to be replaced by any of these numbers which we know will be smaller. So we said at each node in the recursive tree, we're just subtracting all the denominations, and this means it's possible that we're going to reach the same value multiple times. For example, when we subtract 3 from 7, we get to 4, so we solve this subproblem. But then when we have a value of 6 and subtract 2, we also get to 4. This shows an overlapping subproblem. This is why we're memoizing values, to store the smallest number of coins to reach each value. Then if we find it again, we won't continue to recursively call down, and we'll just store the minimum number of coins to reach that spot. So with the top-down approach, the solution to the question is going to correspond to the shortest path from the target to 0. Each time we go to a node, we know that's using 1 additional coin, so the shortest path means we get to 0 in the fewest number of coins, which is also the answer. So here at 11, we subtracted 7 to get to 4, then from 4, we subtracted 2 and 3. When we subtract 3, it's an invalid number because we can't form a valid combination to 1. So at 2, we subtract 2 again, and this gets us to the base case of 0, and then when we find the minimum number of coins at each point, it's 0 at the base case, then 1 here, because 1 is smaller than 99, and we used 1 additional 2 coin. Then, at this point, we used 1 additional coin again, and then we compare that to the other paths. It was 3 for this path after we checked all these recursive cases and kept the smallest number of coins. But then again, we had a 2 path, which is just the inverse of this, where we subtract 2, 7, 2. So then to get to this point is 2 coins. So 2 is the minimum at this level. Then to reach 11, it's just one more coin. So the answer to this question is 3. So to quickly recap, at each point we just subtract all the denominations, and we recursively call this until we reach a base case of 0, which means it's a valid path, or a negative number, which means it's invalid. We memoize the solution to subproblems, and count the minimum number of coins to reach each level. And then once we return to the original call, we know it was just one more coin from any of its children, so we add 1 to the smallest at the level below. Here we incremented 2 to 3, which is the solution. And this was just the inverse of the bottom-up case, where we started at 0 and added up to the target. Here we start at the target and subtract down to 0. And now let's quickly summarize the steps for the bottom-up solution we're about to code out. We start at 0 and calculate the minimum number of change for all the values from 0 up to the target. At each point, we subtract the denomination to find the answer to a previous subproblem, and we take the minimum number of coins to reach that prior spot, and add 1 to it because we're trying to add 1 additional coin to reach the current spot. Once we do this for all the values by making the optimal decision at each subproblem, when we solve for the target, this will also be the overall solution to the question. The big O complexity for this question is O of the D times target time and O of the target space, where D is the number of denominations that we're using, so it's the number of coins that we have available. And the time complexity is D times target because we try all the denominations for all the values from 0 up to the target. Then the space is O of the target because we create a memoization array where we store all the subproblem solutions from 0 up to the target. And now we're ready to write the solution function minCoins for change. This function takes in a denominations parameter, which are the coin values that we have available, and it takes in a target, which is the target change amount that we want a valid coin combination to sum up to. We initialize the coin count for amount array, which is the memoization array that we use to store the solution to subproblems. The length of it goes from 0 to target plus 1. We add 1 since it's 0-based index, so it goes from 0, and the final index is the target amount. And we initialize the values to infinity, which is just the largest number in JavaScript, but you'll use the largest in your language, and this is just a placeholder value because numbers will always be smaller than infinity when we call the minimum function, and if we see an infinity, or infinity is still the solution to the final subproblem, we know there's not a valid combination of coins to reach this amount. We also initialize 0 to 0, so we replace that. This is the bottom condition that we know. 0 is always 0 because the coin denominations will always be larger than 0. So we can set a bottom amount to 0, which is the starting case. So we know in the bottom-up solution, we go from 0 up to the target amount. So 0 to the coin count for amount, which is the memoization array, and the final value is the target we're looking for. So 0 up to the coin count for amount length. Then we just try all the coins at every amount, and that's why we have these nested loops. First, we need to check if the coin is smaller than the amount. If the coin is larger than the amount, then we know it can't reach this amount for any combination. First, we get the current solution to this subproblem, which is the min coins stored in the coin count for amount memoization array, and we access it for the current amount we're at. Then we want to find the minimum number of coins we can use to get to the current amount by using the current coin. So we subtract the coin value from the amount to look up the solution to a previous subproblem. This means we're going from that previous solution to the current amount by using this coin. And at each amount for each coin, we're always trying to add one additional coin to a previous subproblem. So we just do +1 to account for adding this one additional coin to a previous amount. Then we just store the optimal answer for this subproblem in the memoization array for this amount by taking the min of whatever we have currently stored there, or the number of coins it would take to reach this current amount by using the current coin. Whichever is smaller, we store at this amount, and we do this for all the coins at all the values. So we continue to solve the same subproblem over and over, where we're always looking for the smallest number of coins to reach any amount. Once we do this for all the values, we're now able to return the solution. First, we just check if the target is valid. If it's equal to infinity, or the largest integer, then we know it's not valid, and there wasn't a combination that could reach this target. In this case, we return -1. However, if it's not equal to infinity, this means we do have a valid combination. So we can just return coin count for amount at the target. And the solution to this subproblem is also the global solution, because we calculated the minimum number of coins at each step along the way, and then used the solution to these subproblems to continue to build up that minimum coin amount until we reach the target. Then once we try the target value with all the coins, and then use the answer to previous subproblems, solving this subproblem gives us the overall global solution. We run the code and the tests pass. And this question, also known as the coin change problem, is a classic example of dynamic programming. You continue to solve the same subproblem over and over, and you memoize the solution to each. Then at each step, you try all the possible values and use the previous solution to subproblems to locally find the best answer. Then as you continue to build up the optimal solution to each subproblem and solve them all locally, once you reach the end, when you solve for this value, it becomes the overall solution to the question. Thanks everyone, and I'll see you in the next lesson.